तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So we have been discussing the bipolar junction transistor. In the previous lecture, we saw how the transistor can be used for small signal amplification. To summarize the discussion of the previous lecture, the transistor, the bipolar junction transistor, can be regarded as a transconductance amplifier. So as we will see in today's lecture, you can also regard the bipolar transistor as a current amplifier, but fundamentally there are a lot of advantages to be gained if you regard it as a transconductance amplifier. When you regard it as a transconductance amplifier, you can compare it with other types of transistors such as field effect transistors. This point will become clear when we discuss the MOS field effect transistor. Now coming back to this summary, what we said is that this is the basic arrangement for deriving small signal amplification from the device. Here the emitter base voltage is applied and a resistance is included in the collector lead in series with a power supply. The polarities of these two power supplies are such that emitter base junction is forward biased and the collector junction, which is very close to the emitter base junction, is reverse biased, or at most it is zero biased. So we have explained already that you cannot forward bias the collector base junction because then the transistor action is destroyed. Now this is the so called common base configuration. Because both these voltages are applied with respect to the base terminal, which is the common terminal. The other configurations we are going to see in today's lecture. So the bipolar junction transistor, its capability to amplify small signals is more easily understood when you want to derive it from first principles, when you use the common base configuration and you regard it as a transconductance amplifier. So here, if you increment the emitter base voltage, the result is an increment in the collector current. So you have IC plus delta IC, meaning the current IC corresponds to the voltage condition VEB. When you increment VEB by delta VEB, IC increments by delta IC. The increment delta VEB and delta IC are related as delta IC by delta VEB is equal to IC by VT. This is what we have shown. This is the so called transconductance of the device. Now the voltage amplification is given by delta IC divided by delta IC into R. This is a small signal output voltage divided by the input increment, that is delta VEB, and this is equal to Gm times R. This is the voltage amplification. The power supply VCC should be chosen such that VCC is equal to R into IC plus delta IC, where delta IC is the maximum possible increment in IC. So for this limiting case, when VCC is when the value of delta IC is such that IC plus delta IC into R is VCC, this junction will be zero biased, because this voltage and this voltage will compensate each other. Polarity of this voltage is like this. For any other value of delta C lower than the value given by this equation, this junction will be reverse biased. Now that is the summary of what we have done in yesterday's class. Today let us begin by solving an example in which we calculate the values of alpha and beta, the two parameters that we have associated with the transistor action. The problem goes like this: calculate alpha and beta of a PNP BJT having the following parameters. Emitter, the doping level is 10 power 17 per centimeter cube. This is the doping of acceptors because we are considering a PNP BJT. The lifetime of minority electrons in emitter, tau e, is 100 nanoseconds, and similarly the diffusion coefficient of the minority carriers, that is electrons, in emitter is 17 centimeter square per second. The corresponding parameters in the base are doping level 10 power 16 per centimeter cube, minority carrier lifetime 1 microsecond, and diffusion coefficient of minority carriers 11 centimeter square per second. In the collector, the doping level is 10 power 15 per centimeter cube, the lifetime of minority electrons is 10 microsecond, and the diffusion coefficient of these electrons is 33 centimeter square per second. We shall assume that the device has a geometrical or metallurgical base width of 1 micrometer. The temperature is 300 K. Now after calculating the alpha and beta, we also have to calculate, as the problem says, the equilibrium energy band diagram of the device. We have to sketch this diagram. So let us begin the problem. This doping level is 10 power 17 per centimeter cube, and this is 10 power 16 per centimeter cube. Now this is 10 power 15 per centimeter cube. This width is what we have been given as 1 micrometer up to this point. So this is 1 micrometer. Now we need to understand that the electrical base width, that is the base width over which the excess minority carrier concentration is present, is smaller than the geometrical base width, because the electrical base width is the distance between the depletion edges in the base. So here, if these are the depletion regions in the base, then this is the electrical base width. So while this base width is WB prime, this base width is denoted WB. So we need to determine WB. Now evidently this depletion region will depend on the bias VEB, and similarly this depletion width will depend on the bias VCC. What we will do is that we will assume that the collector base junction is zero biased. We will find out alpha and beta for this condition. Emitter base junction has to be forward biased because unless there is a forward bias across emitter base junction, the device is not really working as a transistor. So on the emitter base junction we must assume a forward bias. We will assume a forward bias of 0.65 volts on the emitter base junction. So this we will assume to be zero biased. So the first step is to determine WB, which requires the determination of these depletion widths. So the emitter depletion width here, let us calculate. We will redraw this diagram. So this is P plus plus and N plus base, and this is the depletion region. So this portion and then we need this portion. So this is P. So we have exploded the PNP transistor to show the depletion regions clearly. This is the junction. Now this distance is given to us as 1 micrometer. This depletion region XE, that is a depletion region across the emitter junction, and this depletion region is XC across the collector junction. Now XE is equal to square root of 2 psi naught of the emitter junction, psi naught E, into epsilon, which is the permittivity into the dielectric constant of this region, divided by Q into 1 by doping in the emitter plus 1 by doping in the base. So this is XE. Now what is the psi naught E? The psi naught E, that is the contact potential of this junction, we can find out as at 300 degree K the thermal voltage is 0.026 electron volts, and logarithm of Ne Nb by Ni square. So Ne is 10 power 17, Nb is 10 power 16, and at room temperature this is 10 power 10 into 1.5 Ni square. So this is the contact potential. Now when you solve this, you will end up getting a value of 0.757 volts. So therefore XE we can evaluate as 2 into 0.757. As we have said, we must always include the units also in calculation. So this is volts into epsilon, you know, is 12 for silicon dielectric constant multiplied by 8.854 into 10 power minus 14 farad per centimeter. This whole thing can be approximated as 10 power minus 12 farad per centimeter. Divided by Q is 1.6 into 10 power minus 19 coulomb. The minus 19 we club with this power here. So this is coulomb. And then 1 by Ne plus 1 by Nb. Nb is 10 power 16 and Ne is 10 power 17 per centimeter cube. So if you take 10 power 16 out, you will get 10 power minus 16 here, and this will be centimeter cube in the numerator, and this bracket will be, if you take 10 power 16 out, this will be 1 by 10 because this is 10 power 17, so this will be 1.1. So these are the units. You can see that farad into volt is coulomb, this cancels, this gives rise to centimeter square, so square root of centimeter square is centimeter. Now when you solve this, you will get this is equal to 0.32 micrometer. Please note that we must collect all the powers of 10 and we must collect all the other numbers here. This way you avoid making calculation mistakes. Now this is 0.32. The values indicated here are in microns. Since this is 10 power 16, this is 10 power 17, this is 1/10 of this. I am sorry, this width is 1/10 of this width. So therefore, if this is 1 unit, this is 0.1 unit. Therefore, 0.32 divided by 1.1 is this particular depletion width, and that will turn out to be 0.29 microns. In a similar way, we can evaluate XC and this. It turns out that XC will turn out to be equal to 0.94 microns, and again following the same approach, this is 1/10 of this, so this distance is 0.94 divided by 1.1, and this is 1/10 of that, and therefore this turns out to be 0.085 microns. We can therefore obtain the base width WB, which is this, as 1 minus 0.29 minus 0.085, and that is 0.625 micrometer. Now these calculations which we have done correspond to zero bias across the emitter base junction. As we said, our device will operate with a forward bias across the emitter base junction. So what will happen is, because of that, this depletion width which we have estimated at zero bias will get reduced. Assuming that the forward bias across emitter base junction is 0.65 volts, the new depletion width can be estimated as follows. In this formula, we replace psi naught E by psi naught E minus the forward bias. So this formula will get modified to psi naught E minus forward bias of 0.65 volts. Now when you recalculate the emitter depletion layer parameters using this new value of potential across the emitter based depletion layer, you will get finally this value as 0.11 microns, and as a result this depletion width, this base width will get modified to about 0.8 micrometer. I leave it to you to calculate what is the value of XE for a forward bias of 0.65 volts. Ultimately you will find that this XE will result in the depletion layer on the base side of 0.11 at 0.65 volt forward bias. So this is the base width which we must use in our estimation of alpha. Now alpha is given by, we had discussed this in the previous lecture, we had written down the equation. I will reproduce that equation here. Alpha is equal to the injection efficiency into the base transport factor, which is nothing but 1 over 1 plus, the injection efficiency term is 1 over 1 plus dE by dB, because it is IEN by IEP. So first you have the terms corresponding to the emitter electron current and then the base current. So dE by dB into WB by LE into NB by NE, and the base transport factor is 1 minus WB square by 2 LB square. Now we should substitute the various parameters here. For this we need to know what is LB and what is LE. Now LB is square root of dB into tau b, that is square root of dB is 11 centimeter square per second and tau b is 10 power minus 6 seconds, that is 1 microsecond, and the result is 33 micrometer. In a similar way, if you calculate LE, you will get square root of diffusion coefficient in the emitter, that is 17 centimeter square per second, into the lifetime in the emitter, which we have taken as 100 nanoseconds or 0.1 microseconds. So many centimeters, and this turns out to be equal to 13 micrometer. Now we can substitute these values, and this can be written as 1 minus 0.8 by 33 square into half of this divided by 1 plus dE by dB. dE is 17, dB is 11 centimeter square per second. So each of these terms, d by dB, WB by LE and NB by NE, each of this is dimensionless. WB by LE is 0.8 divided by 13, both are microns, and NB by NE is 1 by 10, because emitter doping is 10 times the base doping. Now this can be simplified, and you can write it as follows. Now first notice that this quantity is really very small. Similarly, this quantity also is much less than 1. It is for this reason that usually this formula in many practical transistors is approximated as 1 minus WB square by 2 LB square minus this term, because 1 by 1 plus x is 1 minus x, dE WB NB upon dB LE NE. So this is approximation, so you can use that here and you will get 1 minus approximately the first term here is 3 into 10 power minus 4 minus the second term is 9.54 into 10 power minus 3. So this term is more than this term, that is what you can see from here. Thus, in modern transistors, the base transport factor is not one which controls the alpha, it is this. Since this is much less than this, even if you neglect it, you will still get a very close answer for alpha to the real value or accurate value. So this is the value of alpha. Now you can go through the calculations and you will find alpha is equal to 0.99, and if you do the calculations for beta, since beta is alpha by 1 minus alpha, that would be 0.99 by 1 minus 0.99, so you will find beta is equal to 99. So let us write down these values. So this is equal to 0.99 and beta it is 99. So alpha is 0.99 and beta is 99. Now the next part of the problem was to draw the energy band diagram at zero bias under equilibrium conditions. So let us do that exercise. You recall that first we should draw the Fermi level as a constant line, then we locate the junctions. So this is the emitter junction, this is the collector junction. Now distance between these two junctions is 1 micron. That is what we have been given. When both emitter base junction and collector base junction are zero biased, then you recall that the depletion width here was 0.32 microns, out of which 0.29 microns was on the base side. So this is emitter, this is base, and this is collector. So 0.29 microns on this side is somewhere around little less than 1/3 of this distance. So we must draw the diagrams to scale. So let us say this is 0.29 microns, and 1/10 of this will be on this side. So let us say this is about 1/10 of that. So this distance is 0.29 and this distance, this depletion width here is 0.32. Similarly, on this side the depletion width is 0.94 microns, out of which 0.085 microns is on this side, because collector is lightly doped compared to base. So 0.085 is about 0.1, 0.1 is 1/10 of this, less than 1/10 of this. So this is about 1, that would be, this is half, and divide this into 5 parts. So this is about 1/10 of a micron and less than that, and 10 times this on this side, so that is about this much. So this distance is 0.94. So this depletion width, collector depletion width, is more than emitter base depletion width, out of which here this distance is 0.085. microns. All values are in microns. Okay, having located the depletion regions, let us extend this EF a little bit more. Now we must draw the conduction and valence band edges. So this is P side and the doping here is 10 power 17. Suppose this is the valence band edge here. So this is EV. So EF minus EV here, this represents the 10 power 17 doping. The doping in the base is 10 power 16. So the distance between conduction band and EF will be more than the distance between valence band and EF here, because this is N type. So we take little bit more. So let us say this is EC. Now coming back to this side, this is 10 power 15 P type. So the distance here will be more than this. So let us take this as EV in the collector. Now we can locate the conduction band edge. So let us say this is the conduction band edge in the collector, and following this we can show the valence band edge in the base somewhere here, and then similarly the conduction band edge here. Now we join as a continuous line the conduction and valence band edges. So this is what you have as the energy band diagram. This potential drop is 0.757 volts, and similarly this potential drop, this is the built-in potential, this potential drop is, we will move this up to avoid confusion, the 0.757, and this is 0.637 volts. So this is our energy band diagram under equilibrium. Let us write it down here. This is equilibrium band diagram of the PNP BJT. Now when the device is operating as a transistor, as we said, the voltage across emitter base junction would be such that it is forward biased. So for example, we have assumed a forward bias of 0.65 volts. So when you want to draw the energy band diagram under forward bias for the emitter base junction, please note that this height will reduce from 0.757 to 0.757 minus 0.65, and similarly the collector base junction may be reverse biased. So in practice, when the device is operating as a transistor, the band diagram will be such that the emitter base junction will have a small variation in the conduction band edge, but the collector base junction will have a very large variation in the conduction band edge. So unlike what has been shown here, here this height is small as compared to this, but when the device is operating, most of the operating conditions, this will be small because this will be forward biased, and this will be large because it will be reverse biased. So band diagram when it is operating would look something like this. So this is the conduction band edge and this is the valence band edge. I have not drawn the Fermi level here. So this is the emitter base junction and here you have the collector base junction. Something like this. So this is the kind of energy band diagram you will see, where this height is built-in voltage minus the applied forward bias, and this height is built-in voltage plus the magnitude of the reverse bias. Okay. So this is band diagram. When the BJT is operating as amplifier. So the collector base voltage keeps changing, so this height will keep changing. The emitter base voltage also keeps changing little bit, so this height may change a little bit, but here the variation will be large because you can have the collector base bias going from 0 to very high reverse biases. Okay. So that is the energy band diagram of the bipolar junction transistor. Now let us look at the operation of the transistor in little more detail. What do our calculations mean? So 0.625 volts is the forward bias across the 0.65 volts is the forward bias across the emitter base junction, and we said that the alpha is 0.99 and beta is 99. What are the kind of currents that will be flowing in this device for this condition? Well, the emitter current IE we can calculate as follows. IE is given by Q into Ni square into, here first we will have the terms for the emitter, that would mean emitter doping and emitter diffusion length of minority carriers, and in the numerator you will have the diffusion coefficient. Similarly, doing the same thing for the base, you will have these terms. For the base you have WB, this into exponential of VEB by VT minus 1. This is the relation between emitter current and the emitter base voltage. Okay, this we know from the p-n junction theory and we have written it down earlier. Now you can substitute the various quantities here as we have done earlier while finding out the alpha and beta. We are discussing for t equal to 300K. So if you calculate this, you will find, incidentally here we must also put the emitter area. Without the emitter area, this would be the current density. So one must never forget the emitter area. Without the emitter area, this is the current density. You can always do a dimensional analysis of this and check that right hand side is amperes per centimeter square. Okay, let us do an exercise here. For example, this is Coulomb, Ni square is centimeter power 6 in the denominator, diffusion coefficient is centimeter square per volt second, doping is per centimeter cube, so it goes in the numerator, and this is centimeter in the denominator. this quantity also will have the same dimensions as this quantity, so we need not consider this. Similarly, this is dimensionless. Now here you find this will cancel, and here you will get centimeter square. Coulomb per second is incidentally we made a mistake here. We can see that because Coulomb per second is amperes, and you are getting this additional volt. This volt should not be there. So this was a mistake. The mistake was that the diffusion coefficient we wrote as centimeter square per volt second. This is wrong. Diffusion coefficient is centimeter square per second. Mobility is centimeter square per volt second. So anyway, we remove this volt and we find that it is ampere per centimeter square. This is the current density. So if you evaluate this, I leave the calculation to you, you will find the answer to be 36 ampere per centimeter square, where this VEB is 0.65 volts and VT is 0.026 volts. So this is the current density, emitter current density, that is the current density flowing here. Now what does this mean? This means that if your device has an area which is 100 microns by 100 microns, if AE is 100 microns by 100 microns, so imagine that this direction, area is in that direction, right? So that area we are talking about is 100 micron by 100 micron. If that is so, then the current would turn out to be IE equal to AE into JE, that is equal to, this is nothing but 10 power minus 4 centimeter square, that is 36 into 10 power minus 4 amperes, 100 microns, this is correct. So 36 into 10 power minus 4 amperes, which is equal to 3.6 milliamperes. So we will assume this as the emitter area, then the current here would be 3.6 milliamperes. So emitter current of 3.6 milliamperes will be flowing here. And how much is the collector current flowing? Collector current is alpha times the emitter current. So 3.6 milliamperes into 0.99, that will give you 3.56 milliamperes. And this base current IB would be beta times smaller than this, or it would be 1 minus alpha times this. So that is 1 minus alpha is 0.01, so 100 times less than this current. So this will be 36 microamperes. Those are the kind of currents flowing in the transistor for this biasing arrangement. Now in practice, this will not be zero biased when the device is operating like a transistor. You will have to put a cell here and you will put a resistance, load resistance, across which you will take the output voltage, and you will make an increment in the input voltage. So small signal will be superimposed over this DC, and as a result you will have small signal over this DC current. Now let us understand what is meant by small signal. The small signal current means the current almost may be about 1/10. In fact, 1/10 is also a very large value. Okay, 1/10 of current is not the DC current is not really small signal. But let us, for practical purposes, assume 1/10 of the current. So this means we are saying 3.56 milliamperes plus delta IC, which is 0.356 milliamperes. So this is the incremental current. Suppose you want to pump in through this lead. What should be the change in emitter base voltage which will produce this change in collector current? We can easily find out as follows: delta VEB is equal to IC by VT into VT by IC into delta IC, right? Because delta VEB by delta IC is VT by IC, or delta IC by delta VEB is IC by VT. We have seen this relation GM into delta VEB is delta IC. So substituting the values, we can find out delta VEB. So you get this is equal to 0.1 times VT, because delta IC by IC is 1/10, that is what we have assumed. So 0.1 times VT, that means you will have to make a change 0.026 volts, or let us write it in millivolts, that is easier to understand, 2.6 millivolts. So 2.6 millivolts increment over 0.65 volts will produce an increment of 0.356 milliamperes in the collector lead, and obviously this will also produce an increment in the base current as well as the emitter current. So these increments here and here also will be 1/10 of the corresponding currents. So this will be 3.6 microamps increment in the base current, and it will be 0.36 milliamperes increment in the emitter current. Now if this is the incremental current present, what should be the value of VCC? The value of VCC should be equal to the resistance R here multiplied by 3.56 plus 0.356 milliamperes. Okay. Now let us take an extreme situation where this current delta IC is exactly equal to 3.56. It is no more a small signal condition, but still let us assume that our device we are trying to operate so that we can get the maximum change in the collector current, okay, and maximum possible output voltage swing. So if delta IC is exactly equal to 3.56 milliamperes, then, and if R is 1 kilo ohm, the value of VCC that you will need so that the collector base junction always remains reverse biased, or at most it becomes zero biased, right? The value of VCC for that condition to be met would be VCC is equal to 1 kilo ohm into 3.56, that is the DC current, quiescent current, plus the incremental current, that is another 3.56 milliamperes. So which is equal to 3.56 into 2 volts, right? That is about 7.12 volts. That would have to be your VCC. So this is a numerical example illustrating the operation of the transistor as a small signal amplifier. Now as we have said, this is the common base configuration. Because the base is common, and this is the emitter is the input and collector is the output. Instead we can have common emitter configuration, right, where you can not only get the voltage gain that you are getting here from emitter base junction to the collector lead, you can also get a current gain. For example, here the collector current is alpha times the emitter current. Actually there is a slight fall in the output current as compared to input current. This is input, this is output. So you are not really having a current gain, you are having a current loss. You are however having a voltage gain that we have seen, or a transconductance gain. If we use the base lead as the input terminal instead of the emitter lead as the input terminal, and continue to use the collector as the output terminal, then clearly from base to collector there is a factor of beta increase in the current. So we will be able to get the current gain also in addition to the voltage gain. So the configuration for common emitter would be as follows. Let us modify this same circuit to make it common emitter. How do we do that? The emitter should be common, right? So collector should be connected to emitter through this. So we remove this from here and we put it here. Now when we do that, this current here will not be 3.6 milliamperes obviously, because this is emitter current. So this 3.6 milliamperes is actually the current in the emitter lead. So that is going to be 3.6 milliamperes, and the current in this lead here through the cell is 36 microamperes. Okay, so the currents, these currents are not going to be affected so long as the collector base junction is zero biased or reverse biased. That is the assumption. Okay. Now you may say that when the collector base junction is reverse biased, then what about the IC naught? Okay. Should we not add IC naught here, because this we have calculated for zero bias condition? Yes, when the collector base junction is reverse biased, we must add the current because of IC naught. In fact, the current that you will have to add when in the common emitter configuration will be slightly different from the current you need to add in the common base configuration. But since IC naught is small, okay, we have neglected it. We will justify this approximation later on. So right now let us not get into the effect of IC naught. So long as you don't get into the effect of IC naught and you maintain zero or reverse bias across the collector base junction, if you maintain 0.65 volts across the emitter base junction and your device has an emitter area of 100 microns by 100 microns, then for the other doping and lifetime and diffusion coefficient conditions, you are going to have the same currents flowing in the device. However, now when you make a change of 0.026 volt, 2.6 millivolts here, you will get a change of 0.356 milliamperes here, and there will be a change of 3.6 microamps here. If you now try to find out the power gain of this, then your power gain will be as follows. The input terminal is this and the output terminal is this. So delta IC by delta IB is a small signal current gain for the common emitter condition. The voltage gain is given by the previous formula, that is Gm into R, that we derived. The voltage gain is Gm into R. Gm is the transconductance of the amplifier and R is this resistance. So this Gm is nothing but IC by Vt. So delta IC by delta IB into IC by Vt into R. So delta IC by delta IB is nothing but beta. So this is the power gain. in the common emitter mode, okay, whereas the power gain in the common base mode was alpha times IC by Vt into R. So this is common emitter, CE stands for common emitter, CB stands for common base. Now since you get a power gain in the common emitter configuration, that is this configuration, it is this configuration that is used most often for signal amplification. The common emitter is used most often for signal amplification. So 3.6 microamps to 0.356 milliamps. So input is 3.6 microamps, output is 0.356 milliamps, okay. So current gain is there. In addition, anyway you have voltage gain, because when you pass this through the resistance R, if it is 1 kilo ohm, then 0.356 milliamps into 1 kilo ohm, that is the output voltage change in response to this input voltage change. Now let us build up from here the normal common emitter amplifier circuit that we see with many more resistors than this. That can be built up very easily from here as follows. So we will draw the same circuit using the symbol of the transistor first. So this is the emitter junction, or let us draw it below this first. We will remove these quantities. So first we convert this into a symbol. Now what we will do is we will turn it 90 degrees, because that is the way we often see it in the books. Now here you have the resistor, and here you have the power supply. Now you will have to superimpose the AC over this. So this is equivalent to, in equivalent circuit terms, putting a AC source here, okay. But in practice doing this is somewhat difficult, to put a source in series with another source. There is a better arrangement to do this. Now for that purpose, what we do is we modify this whole circuit a little bit on this side. First, for the DC conditions, instead of having one power supply here, another here, since this power supply is smaller than this power supply, we can derive this from here as a resistance divider. So from this power supply we use a resistance divider to get this voltage here, required voltage, and now this we use as the input terminal, and we couple the AC voltage through this capacitor, coupling capacitor. This coupling capacitor provides DC isolation between this point and this point. Similarly, the output is then taken from here through another coupling capacitor, okay. This is the output. So this is the so called VCC. This is the load resistance RL. This is R1, R2, R2 by R1 plus R2 into VCC is the so called VEB here, okay. Now this will not provide you a stable current, because you are fixing the voltage here. So this is VEB. Try to fix the voltage. If the temperature changes, then the current will change rapidly. So what do we do? This we will see in the next class.